right, so this is section 1B, part 2. Sorry, I accidentally turned off the previous one right in the middle of this. Not in the middle, I guess I was just starting this example, but let's just quickly review. We are ready to actually find a limit numerically. We're going to start by looking at the limit as x approaches 0 for the function sine x over x. Now we'd like to do this numerically, so we're going to approach 0 using that same strategy that we just described. So I'm going to go ahead and I'm going to almost treat this little chart that I've made here like a number line. And I'm going to say the x values are approaching 0. So I'm going to put 0 right in the middle. And then I'm not going to attempt to make this to scale. I'm just going to pick x values like we were doing before. I'm going to say 1/10 to the left and 1/10 to the right of 0. And then 1/100th to the left, and 1/100th to the right, and 1/1000th to the left, and 1/1000th to the right. So I've got the x values that I'd like to investigate. Next, I'd like to find the y values that go with those. And in order to do those, I just need to take these x values and plug them in here. You can do that using a calculator table. I'm going to do it using a Desmos table just because it's easier for you to see Desmos on my computer than it is to see the calculator screen. But you can use whatever technology is handy. Of course, you could individually plug in the points as well, but that's going to be kind of a pain. So I'm going to go ahead and pop over to Desmos here. Let's see. It's just desmos.com. And since we are using trig, you're going to want to double check over here on your little wrench. Make sure you are in radian mode. And I am, so I'm good here. And my function is y equals sine x over x. Now it does give me a graph automatically. I'm going to ignore that for now, although it's handy. We'll be able to kind of make some comparisons later. And I'd like to instead get a table of values. So I'll go ahead to this little gear here and ask for a table of values for my function. And then I'm just going to plug in those x values that we said we were interested in. Starting with -0.1, -0.01, -0.001. I'll go ahead and put 0 in here, even though I know it's going to turn out to be undefined, right? 0 in the denominator is a problem. Then on the other side, I'd have, positive 1/1000th. I cannot type. Let's try that again. There we go. And 1/100th and 1/10th. There we go. All right, so I've got these y values, and all I'm going to do is take those y values and I'm going to transfer them into the chart in my notes. So I'm going to go ahead and do that. I'm going to pause, do that, and then we'll come back and take a look at that chart. All right, so here we go. I've got my values from that table that I created in Desmos just copied into my chart here. And I'd like to investigate the pattern. Again, finding a limit numerically is all about pattern. So notice what happens here. X is approaching 0 from the left on this side. And I'm going to notice these y values seem to be getting closer and closer to 1, right? 0.99 and then 0.9999, and now there's 6 nines. So I can see that the y values appear to be approaching 1. I need to verify that that is either the same or different from the other side. So on this side, my x values are approaching 0 from the right. And once again, as I get closer and closer to 0, it appears that my y values are getting closer and closer to 1. So I'm feeling comfortable at this point saying the limit as sine x over x as x approaches 0 seems to be 1. All right, next I'd like to find the limit as x approaches infinity for sine x over x. So again, I'm going to select x values, and this time I just want my x values to get bigger and bigger. So I'm going to take 10, 100, 1,000, maybe 10,000. I probably don't need to go any further than that, although we can if we want to. But notice we're setting up our x values. X is approaching infinity, just like I want it to. All right, I'm going to go back to Desmos again, and let's get some y values to go in there. And let's see here, I want 10, 100, 1,000, 10,000. We can see it's getting really, really small here. So once again, I'm just going to take these y values and I'm going to go ahead and plug them into my chart, my written chart, so we can take a look at the pattern. So here we go. I've got my values from the table written down in my chart here. And I did change my scientific notation into standard notation just to make it a little bit easier to see. But let's see what happens to y here as x goes to infinity. I've got negative 0.05, negative 0.005, and then 3 zeros and then an 8, and then 4 zeros and then a 3. The signs do change from positive to negative, but notice here, this is in the hundredths. Here the first non-zero digits, the thousandths, the 10,000ths, the 100,000ths. These values are coming closer and closer to 0 all the time. So I believe that the limit of sine x over x as x goes to infinity is 0. All right, we have one more. I'd like to find the limit of sine x over x as x goes to negative infinity. So this time, oops, sorry, I didn't label my y here. My x values need to approach negative infinity, so I'll just go with negative 10, negative 100, negative 1,000, and so on. And I can go back to Desmos again and just throw some negatives in here. And it looks to me like those values actually didn't change at all. They look identical to what they were before. So we'll go ahead and we'll just transfer the values into our chart. They're exactly the same, so maybe I won't even bother keeping quite as many decimal places. Same idea. Every single time, the first non-zero digit moves further and further to the right. So as x is approaching negative infinity, these y values are approaching 0. And once again, I can say that 0 is going to be my limit. All right, we've got that much. We're going to try to use these to predict what the graph's going to look like. Now, we've actually already seen the graph a little. We cheated a little bit using Desmos here. But let's go ahead and talk a little bit about what's happening. And we're actually going to try to improve on the graph that the calculator gave us, just a little bit. So first of all, I know that when x is 0, the function value itself is undefined, but the limit is 1. So I'm going to go ahead and say, let's see, 1, 2, 3, 4, 5. Let's call this 1. And oops, sorry, I got to pull that up so you can see it. I'm going to say that when x is 0, since the y value doesn't exist, I can't put an actual point on the graph, but it does have a limit of 1. So that tells me that there's going to be a hole in this graph at the point when x is 0 and y is trying to be 1, but really isn't quite. Now I know that as x goes to both positive and negative infinity, the limit is 0. And so I do know that as I come away from this point, I should be going down towards 0 on both sides. That's describing a horizontal asymptote. So I'm going to go ahead and sketch in a horizontal asymptote, and I'm going to ask in this class that you be very explicit about your asymptotes. I want you to always draw them in as horizontal lines to make them very clear to me as your reader. So I'm going to go ahead and put in a horizontal asymptote at y equal to 0. And I know that my graph has to approach that horizontal asymptote out at the end behavior, at the negative infinity and positive infinity ends. Now, because this was a sine function, it didn't just sort of come down and get close. It actually did some oscillating, right? If we went back for a moment and looked at the Desmos graph again, remember how it went negative and then positive and negative and then positive? But the oscillations per se are smaller and smaller all the time. In fact, if I changed my axes and went negative to 100 to positive 100, and let's see, I'm going to make the y-axis just negative 1 to 1. I can really see what's happening there. There's that, looks like a sharp peak. In fact, you know what? I want to make that 2 instead of 1 so it's a little bit more clear what's going on. There we go. All right, so I can see that I do have the highest point here at 0, 1. We know that that's really an empty circle, even though the graph doesn't draw it that way. And then you can see how asymptotically we're approaching 0 on both the left and the right side, not in a smooth way, but by the virtue of the fact that these oscillations get to have smaller and smaller amplitudes as time goes on. So I'm not going to draw this many oscillations on my picture, but let's go ahead and try and sketch at least a little bit of what this looks like. I'm going to cheat just a little. I'm not going to give us a scale on the x-axis. Instead, I'm just going to say, based on what I see, this just oscillates in such a way that it gets closer and closer. I'm going to be about the same here. Try and get the symmetry in there. So that I can see that it is approaching the horizontal asymptote. It's just oscillating on the way. By the way, notice that you can cross a horizontal asymptote. If you think about what asymptotes or horizontal asymptotes come from, they come from these limits. It shouldn't be a surprise to you that it's okay to cross them. What does this limit say? It says way out at negative infinity, or this one up here was for positive infinity, right? The y value approaches 0. This limit doesn't tell us anything at all about what happens for smaller values of x. This graph can cross the x-axis as many times as it wants to. And in fact, it's going to cross infinitely many times, right? It's going to keep on oscillating. But ultimately, it does approach y equals 0, the x-axis in the long run. So it's because horizontal asymptotes come from limits at infinity and negative infinity that they only tell us about end behavior. They don't tell us about anything for smaller values of x. You can cross those horizontal asymptotes as often as you need to. All right, let's go ahead and do one more in this video, and then we'll finish up in a third. I'd like to go ahead and take a look at another function here. We've got the limit as x goes to 0 plus and minus infinity. And this time our function is 15 over 3 plus e to the 1 over x. So once again, my goal is to approach 0. And so I'm going to pick the same values as I did last time. I'll start 1/10 away, and then 100th, and then 1,000th on both the left side and the right side. So I'm letting x approach 0 from the left, and I'm letting x approach 0 from the right. Let's see what happens to the y values in this case. And once again, I'm going to go ahead and use Desmos just to go ahead and give us an easy, quick way of filling in our chart. Our function this time was 15 over 3 plus e to the 1 over x. And again, I'm going to use my little gear shift here to make a table out of that. And then I'll put in the x values that I want in order to create some kind of a pattern, I hope, that's going to allow me to get close to 0. All right, so some interesting things are happening. And, again, I always want to warn you, you got to take what calculators give you with a grain of salt, right? In this particular case, this says that at x equals 0, the y value is 0. Is that possible? I don't think so. If I come up to my function, if I tried to plug 0 in for the x value, when x is 0, we have 0 in the denominator of that fraction. So in fact, even though the calculator tells me 0, I know that that's undefined. I'm going to go ahead and put the other values into the table. So here we go. I put my values into my table here. And this, again, is a good example of a time where we have to use what we know to kind of interpret what the calculator was telling us. The calculator, first of all, when x was 0, told us the y value is 0, but we know that can't possibly be true. 0 in the denominator of that fraction would make that undefined. So I changed that to does not exist. As x approached 0 from the left, I had this 4.9999, and then I just said 5 after that. These are probably rounded values. Probably it was 4 many nines, so many that Desmos couldn't hold them. So they just rounded it up to 5. But even still, it seems pretty clear that y is approaching 5. Now on the other side, as x approached 0 from the right, I had 6.8 times 10 to the negative 4th, and then 5.58 times 10 to the negative 43rd. That is a really tiny number, right? A decimal point with 42 zeros and then the 558. This probably, again, wasn't really 0, but couldn't hold it. It rounded it to 0. And these numbers are clearly approaching 0. So y is approaching 0. All right, so in this case, I don't get agreement from the left and the right. And so I'm going to have to say that this limit itself does not exist. But what I can say is something about the one-sided limits. The limit as x approaches 0 from the left, and I'm just going to say of f of x for this function, we know we're talking about that one, is 5. And the limit as x approaches 0 from the right for this function is 0. I'm expecting then that kind of a jump in the graph because the two sides won't connect, right? They come to different limits. All right, let's just kind of quickly go ahead and plug in some values to get the limits as x goes to infinity and negative infinity. If x is going to infinity, I'm going to go with 10, 100, 1,000, 10,000. And I'm going to do negative infinity at the same time. So here we can clearly see our x values are getting very large. X is going to infinity. And here, x is going to negative infinity. I'm going to go back to Desmos and plug those values in. So first of all, I had 10, 100, 1,000, and 10,000. And you know what? I'm looking at these values, 3.65, 3.74, 3.749, 3.7499. Let's try one more. Let's do 100,000 because I'm thinking that I kind of know what's going on, but I want to prove it to myself. Yeah, you see how that's going? The 3.74 is staying the same, and each time there's more nines. That looks to me like it's trying to reach 3.75. So I think we'll be able to say that's our limit. Let's go ahead and try the negative ones as well. And there we go. These looks like it starts out a little bit above 3.75, but notice here 3.75 with 1 0 after it, and then 3.75 with 2 zeros, 3.75 with 3 zeros. The amount over 3.75 seems to be getting less and less each time, so again I think we're probably approaching 3.75. I'm going to translate those values over to my chart on paper. So this is a really good example of why we really need to see a pattern. Again, here are my y values, and they appear to be trying to reach 3.75, but not quite. So I'm going to say it looks to me like the y's are approaching 3.75. And so that would be my limit. And the same thing here. These y values, although they start a little bit bigger, they still seem to be trying to come down towards 3.75. And so once again, that's my limit. Seeing that pattern is really important when you do numerical limits. All right, so let's think a little bit about this. I kind of deliberately didn't adjust my viewing window on the graph because I'd like to try to predict what things are going to look like here before we take a look at the Desmos graph. So I'm expecting to see a jump here at the at x equals 0. And in fact, that jump at x equals 0 is going to approach 0, 5 from the left and 0, 0 from the right. So let's start by putting that much information in. I'll go ahead and assume that these are just all ones this time. So 1, 2, 3, 4. Well, actually, you know what? Let's go with halves. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm going to call this 5. So this is 1, 2, 3, and 4. And negative 1, negative 2, negative 3, negative 4. Like so. And I'm expecting to approach 0, 5. Open circle from the left, and 0, 0, open circle from the right. Remember that the y value does not exist at 0, so neither one of those can be solid circles. They both have to be open. All right, the limit as x goes to negative infinity, and it was the same for positive infinity, was 3.75. So those are going to be horizontal asymptotes, right? That's end behavior. The graph should get closer and closer to leveling off at y equals 3.75. So horizontal asymptotes at 3.75, let me draw those in. Let's see, 3.75, 1, 2, 3.75 would be here. And again, asymptotes are a big part of working with limits. So I'm always going to ask you to indicate your asymptotes very clearly with dotted lines. All right, our graph actually, we can predict very well what this is going to look like. As we went towards negative infinity here, notice that the graph approached the graph approached 3.75 from numbers a little bit above it. And then up here, it actually approached from numbers a little bit below 3.75. So if I kind of put all of this information together, I've got a pretty good idea of what's happening here. At negative infinity, I'm a little bit above 3.75, and then I'm approaching this hole here at 0.5 from the left. So I'm expecting a graph to kind of look like this. On the other side, I was a little bit below 3.75 on the right, near infinity. And then I'm approaching this hole at 0, 0. So even without looking at a good graph on Desmos, I have a pretty good idea of what this graph is going to look like. I've got this jump right here at 0. I've got the approach of the asymptotes. And going to 0 from the left, I approached 5. Coming to 0 from the right, I'm approaching y equals 0. Let's verify that with our Desmos graph, and here it is. I'm going to go ahead and change my values here this time, my window, so I can see this a little bit better. Let's go ahead and go from, I don't know, we'll go from negative 5 to 5 on the x-axis. I'll change that if I don't like it later. And we'll go from negative 5 to 10 on the y-axis. And just see what that looks like. And there we go. Here at 3.75, you can see the asymptote. In fact, if I want to, I can even graph y equals 3.75. I'm just graphing the asymptote to make it a little bit more clear. And so we can see coming towards 5 from the left, and then approaching the horizontal asymptote over here at negative infinity, approaching 0 from the right, and then the horizontal asymptote again approaching 3.75 towards positive infinity, just like we predicted based on our limits. All right, we will stop there and we'll come back with one last video to finish out this section.